Afternoon, everyone. I'm recording this video for Thursday, which would be March 7th. I will see everybody on tomorrow, Friday, March 8th. But hopefully, with this last bit of information, we'll have covered all of the content. So this will kind of conclude Unit 7. That way, tomorrow we can recap what was on this video and clear up any confusion here. First off, since we're going to be talking about standing waves in a tube today in this video, as well as intensity of sound, I want to start with a recap of standing waves in a string, just because strings and closed tubes are very closely related. And the core idea really behind almost all of these formulas for standing waves is a few things. It starts with this idea of, or the equations at least, start with our basic wave equation, right? Velocity is frequency times wavelength. And what happens in a standing wave is certain and specific frequencies, when they match the certain boundary conditions of whatever our setup is, if we have a certain frequency that produces a certain wavelength that will allow us to match our boundary conditions, we'll see a standing wave form. And so the question is then, well, what are those certain frequencies and what are those certain wavelengths? Well, the frequencies can really be just about anything. They're going to depend on a number of things. It's going to depend a lot on the speed of the wave, and it's going to depend a lot on what wavelength is required, right? So it's a string. So let's kind of pull our equation out. And for strings, we have a different formula for this velocity, right? For the velocity of a string, we know that the velocity is the square root of the tension in that string divided by the linear mass density of the string. So this is just one of our equations that's listed on our formula sheets. Let me write that a little bit better. So that's our equation for velocity. And then our frequency is going to really change, quite a bit based on, let's see if I can move this over a little bit. Let's move. Actually, let's move this here up. So there we go. So our frequency is going to depend on next really what the which harmonic we're looking at. So this, we're going to say this frequency, let's put it here, is going to be some frequency of the nth harmonic. Could be the first harmonic, the second, the third, the fourth, the fifth, and so on. So we'll see, which harmonic we're talking about. And so then the last piece of this equation is the wavelength. So where do we find the wavelength here? Well, first string, these are the patterns that form on the first through fifth harmonic. We could, of course, go higher up, but this is enough for now. And you should see a pattern emerge, right? If we wanted to measure a wavelength and we look at these standing waves, we'll notice that a string that's fixed on both ends does need to have a node at the top and a node at the bottom. And looking at these patterns, one wavelength is going to be equivalent to two antinodes. When we look at these patterns, two antinodes here is the equivalent of one wavelength. So then how do we determine the wavelength? Well, the wavelength is going to be a fraction of the length of this string, right? So this is a distance measurement. So if we need the wavelength, we need what we're going to call L, which is how long is the string? And so what fraction is that going to be? So with our first harmonic, we might note that the wave pattern here is not even a full wavelength, right? It's actually half of a wavelength is going to be the length of this string. So our formula that would calculate out wavelength for this one, in this instance specifically, would be 2L. Really, we're going to say 2 over 1, right? Times the length of the string. That's our wavelength for this fundamental first harmonic. If we look here at the second harmonic, what is the wavelength? Well, it is the length of the string, just L, right? Well, I want to kind of keep a pattern with our equation so we can see where it comes from. So we're going to say 2, because it takes up 2 antinodes, makes a wavelength, and there are 2 antinodes present. So 2 over 2L. There's just one L, right? The wavelength is the length of the string. And now the pattern becomes a little more obvious here. What about the third harmonic? Well, our wavelength is now 2/3 of the length of the string, right? 2 of these antinodes out of the 3 that are present. So 2/3 the length of the string. And then the 4th harmonic is 2/4 or half the length of the string. And the 5th harmonic, we have 2 out of 1, 2, 3, 4, 5. So 2/5 the length of the string. So what is our pattern? What's our formula for the wavelength if we want to set a general equation? Well, our general equation is 2 over n, and n in this case being which harmonic we're looking at, right? 1, 2, 3, 4, 5. So 2 over n times the length of the string, and that's going to be our wavelength. Now, if you look on your formula sheet and how it's written on the board, although this is the equation and where it comes from, it's rewritten slightly, right? We're solving for the equation is written as if we were solving for the frequency. So if we divide both sides by 2 over NL, we end up with the equation that you'll find listed on your formula sheet, which is listed as N over 2L. So we're just taking the reciprocal of this function for the wavelength, N over 2L times the square root of the tension over mu equals our frequency of the nth harmonic, right? So this is our equation, and that's where it comes from. It's just pulling off this wave equation, but the velocity of a wave, of a stringed wave on a string, and then the wavelength based on these boundary conditions, right? And so that's how we found and calculate our equation for standing waves on a string. We've looked at that in class already. So now what about tubes? So we're going to look at standing waves of a tube here real quick. And the boundary conditions are a little bit different. The formula is going to be, whoops, let's try that again. There we go. The formula is, or at least our base formula is still the same. So the speed here is going to be, whatever speed we're looking at. Typically, this is going to be the speed of sound in air, because usually we're vibrating a column of air in this tube. And we do have an equation for speed of sound in air, right? It's 331 at 0 degrees Celsius. And then if temperature is different, we take the square root of the temperature in Kelvin over 273 to find how much the temperature has affected that speed of sound. But we're not going to put this formula into our equation. We'll just leave it as V. This is the speed, and we'll just leave it there. Frequency is still going to be frequency, right? So we're not going to really make much changes to our wave equation. We'll keep this as V equals, we're going to say frequency is going to be, well, whatever harmonic it is. The frequency of, again, the nth harmonic. And now, just like we did with strings, we need to find what is our pattern, what is our formula here for wavelength. So just like in strings, we'll probably have a length, not of a string, but the length of our tube. We'll call it L. And in this time, our tubes are going to be fixed at one end, or that we have a closed tube. We could write a similar equation for an open tube, but I won't go into that just because it's not on your formula sheet and you're not going to be asked any questions about it. The formula is following the same idea, it's just a slightly different equation. So what does that mean? Well, at a closed end, we need a node. And at an open end, we want that sound to come out the opening of that tube nice and loud. So we're going to have an antinode, constructive interference areas at the top. So what pattern is going to emerge with a node at the bottom and an antinode at the top? Well, it's going to look something like this right here. And so what is the wavelength here? Well, this is, remember, 2 antinodes make up a full wavelength. And this isn't even one whole antinode. This is only a fourth of an antinode. So what is the pattern that's going to emerge here? Well, it's 4 over 1 times the length of the tube. Okay. So then we would say, all right, well, what's next? What's going to form next? And if we look at the next pattern that emerges, the next pattern that has an antinode at the top, I'll keep it in red, I guess. We want an antinode at the top and a node at the bottom start here. I need something like this as our pattern. And so what is this pattern? Again, we are not at a full wavelength here, right? This is 3/4 of a wavelength. So how would we calculate what an actual wavelength is? Well, in this case, we want 4 antinodes, 4 of these little half antinodes, I guess, but we only have 3. It's only 3/4. So 4/3 of the length of our string tube here, meaning just an extra little third piece up here, right? You could imagine an extra little quarter up here needs to be added. And so 4/3 of the length of the tube here would form our harmonic. And then what about the fifth? What about the fifth? Well, we do the same thing, right? And it looks like this as such. So what do we have here? Now we have 1 and a 4th, right? So here would be 1 harmonic. This is 1 harmonic, and then an extra 4th. So 1 and a 4th. And so we have 1 and a, what's 1 and a 4th? Well, our wavelength is not, this is 1 and a 4th wavelength is present, but we just want to find the equation for 1 wavelength. So that is going to be, what are these? 4 of these little quarter waves, right? So 1, let's use this here. We've got 1, 2, 3, 4 out of 5 total of these little quarter back and forth movements. So our equation is going to be, how much is this piece right here? This is 1 wavelength, right? Well, that piece is 4/5 L. And again, you should see a pattern here. Our wavelength is going to be 4, here's where our equation's different, over N times L. But you maybe noticed we actually are missing something that we had in a standing wave. There's no second harmonic. There's no 4th harmonic here, right? It's 1, 3, and 5. And the reason is that we have an antinode at the top and a node at the bottom. So because those are different, we are not going to be able to have any even harmonics. All of our harmonics for a closed tube are always going to be odd. So what's the equation? Again, this is where it's coming from. How is it listed in your formula sheet? Well, it's just changed slightly differently. They're solving not for the speed of the wave, they're solving for the frequency at the nth harmonic. So again, we'll divide by 4 over N times L, and we get our equation of NV over 4L. And so this is our equation for a tube. And conceptually, it's the same thing that's happening with the string. It's just that the boundary conditions are a little bit different. So our formula is shifted just so much. And then for the N values, remember, there will not be any odd values. We have 1, 3, 5, 7, so on and so on and so on. And so we'll always only have odd harmonics for our tubes. Just in case it comes up, I'll also mention one other setup. The first harmonic, we're really always going to call this our fundamental harmonic, right? Our fundamental frequency. And a lot of times what you're going to call these ones above it, the overtones, right? So for a string, if you see a phrase about an overtone, that's how many harmonics it is above or over the fundamental, right? So the first overtone might be the second harmonic here in a string, and the second overtone might be the third harmonic in a string. So overtones, if you hear that phrase, that means how many over the fundamental it is, just in case that phrase pops up anytime you're seeing it, is what an overtone would be. All right, so that's all about standing waves. There's one last piece that I want to look at as well, and that is sound intensity. So sound intensity. All right. So here's sound intensity. And sound intensity is essentially our volume. We talk about volume being a measurement of amplitude, but really it's a little bit more than that. A large amplitude is going to mean a large volume, but intensity is a little bit different. So intensity we're going to represent with a capital I. And intensity at its core level is the amount of power over an area, right? So if you have a really powerful sound, a really loud sound over a really small area, you can have a really intense sound, right? So, but if the area is small enough, you don't even have to have that powerful of a sound to make a really intense or loud noise, right? If you have headphones, they do have a power output, but certainly not that loud. But since you're putting your earbuds directly into your ear, the area there is really small. So when we have a very small number on the denominator, if we put headphones in, we can have a pretty intense sound, a pretty loud sound. Don't want to make it too loud and damage your eardrums, right? So because it's power per area, power is measured in watts, area is measured in meters squared. So the units for intensity, or at least one of the units for intensity, is a watt per meter squared. And there are a few values here that might be important to know. And one of them is called the threshold of hearing. The threshold of pain is another one that's going to be listed on your formula sheet. You don't need it for any calculations. It's just an upper limit where higher than that intensity, and you're going to start, physically hurting when you hear that sound. The threshold of hearing is the one that is important. That is the one that you're going to, see show up. And the threshold of hearing is basically, this is the softest sound that you can make out. Any less intense of a sound, and there's not enough power there for you to hear it. It's imperceptibly quiet. And so the threshold of hearing, we're going to call it I naught. This is the smallest intense sound that you can hear, is 1 times 10 to the negative 12 watts per meter squared. Right? And so that number is going to come to play in just a little bit. But what is this area, right? What is this area? Well, if we think about sound, if we speak, if we make a sound, we hit something, pluck a guitar string, sound an instrument, we have some source, right? How does that sound radiate out? Well, it radiates out in a circle, right? Bigger and bigger and bigger, but it's not just a circle. We're dealing with a 3-dimensional space, right? We don't deal in just a 2-dimensional surface. We exist in a 3-dimensional world. So how does that sound radiate out? It radiates out as a sphere. And so we have intensity, yes, is power per area, but what is that area? Well, what's the area of a sphere? It is pi, 4 pi r squared, right? So 4 pi r squared, you're going to see that equation show up on your formula sheet. And I think it says intensity due to a point source. And the reason for that is because it spreads out spherically from some source, right? And so might occasionally say, oh, I'm so far away from some source of sound. What's the intensity? Because I'm so certain distance away. Well, the power of that sound, how much energy we input into that sound, divided by 4 pi r squared. R would be how far away we are from the source, can help us find that intensity. But if we're talking about loudness, we're talking about volume, we're talking about intensity, you see watts per meter squared, you say, wait, I know a different unit of measurement for volume you may have heard before. And you say, well, yes, of course, there is one more. Why is this so small? Okay, let's do this. All right. And there is another unit for sound. The other unit for sound is the decibel, the mighty decibel, dB. So this is the decibel. And we have really 2 units of sound measurement, the watts per meter squared and our decibel levels. And decibels, however, is a little bit tricky because it is not a linear scale. It is a logarithmic scale. It's a log base 10. So meaning if I go from 10 to 20 decibels, what that means is that sound intensity has increased by a factor of 10. 20 decibels is 10 times louder than 10 decibels. But what about 30 decibels? Well, 30 decibels is also 10 times louder than 20. And 40 decibels is, you guessed it, 10 times louder than 30. So what about from 10 to 40? What would that? Well, 10 to 20 is 10 times. 10 to 30, if we increase our sound intensity by 20 decibels, it's not 20 times louder. It's actually times 10 to get to 20, and then times 10 again to get to 30. So times 10 times 10, 10 squared, 100 times louder. So 10 decibels and 30 decibels, that's 100 times louder. And from 10 to 40, would be 10 cubed, 10 times 10 times 10. So 1,000 times louder. So this is not a linear scale. It's called a logarithmic scale. And if you've dealt with logs in your math class, maybe you have a little bit of knowledge on that. So what are you going to be asked to do in here? Great. I understand how, I don't know why that didn't pick up. So let's try that. So what do we do? How do we do this? Well, the only thing you'll really be asked to do for the most part in this case is how do we convert between watts per meter squared and decibels? And it's really just a unit conversion equation. So I'll give you the unit conversion equation, and there'll be times where we need to convert from watts per meter squared to decibels. There'll be times where we need to convert from decibels to watts per meter squared. We want to make sure we know how to do both. The equation for this conversion is right here, beta, and this is going to be our intensity in decibels. So I'm going to put I in decibels, right? So if I want to know what is the decibel level, we calculate that by 10 times the log. You want to make sure you know how to use log function in your calculator, times I, which is the intensity we're wanting to convert, right? So if I say, oh, well, the sound has an intensity of 1 times 10 to the negative 6. What's the decibel level there? Well, that 1 times 10 to the negative 6 is my intensity. I'd put it in this I value here, and throwing this into this equation would output me a value in decibels. But we also have one last piece, and that's divided by I naught. And here's where this I naught, remember, we mentioned it earlier, that is going to be this threshold of hearing right here. 1 times 10 to the negative 12. So this is not so much as a formula we're calculating with, it's a unit conversion. We either have a value in watts per meter squared and saying, what's the decibel level? Or we're going back the opposite way. So the equation in your formula sheet is set up to just plug numbers in and output a value in decibels. But what if you have to solve for it the other way? What if we say, well, I have a 45 decibel sound. What's the intensity in watts per meter squared? And in that case, we're just going to rearrange this equation and solve for I. And in case you've forgotten how to rearrange an equation, that is a log, and this is actually a log base 10. I can't remember if they list the 10 on your formula sheet or not. But either way, it is a log base 10. So that's what we need to know. Yeah, I'm certain it would. It would be kind of weird if it didn't. How do we solve for I? Well, let's move everything but the log first. So we're going to rewrite this equation just a quick way. This is in your formula sheet, but what if I want to solve for I? What's that formula going to look like? And maybe you already know how to do this, in which case, great. You don't have to watch the last part of the video because this is the last thing we're going to look at. So what do we do here? I over I naught. Well, the first thing is I'm going to move this 10 over. And how do we do that? By dividing both sides by 10, right? And that's going to give me, we'll move this down here. It should be a beta, not a B. Beta means our decibel level divided by 10 equals log base 10, the I over I naught. So then here's where we forget. How do I get rid of a log base 10? Well, it's very simple to do. All we have to do is raise both sides to the power of 10. So 10 to the power of beta over 10 on this left side. And if I put 10 to the power of log base 10, that cancels this out. So 10 to the beta over 10 equals I over I naught. And then finally, what is I? Well, it is I naught, so the threshold of hearing, times 10 to the power of our decibel level divided by 10. So this equation right here is not one listed in your formula sheet, but I would make sure you either know it or know how to pull this out of the equation that is on your formula sheet, because you will need occasionally, what if you get that question? All right, we have an intensity of 45 decibels. What is that in watts per meter squared? Right? How do we find that value? Well, this is the equation here that you would need to find that intensity in watts per meter squared. All right, so that is it for our video and it for unit 7. So again, in this video, we looked at standing waves in a string. We looked at those patterns that emerge and how that formula came to be. We related that also to standing waves in a closed tube, and found the formula that's tied to that, only odd harmonics forming in a closed tube. There is a very similar formula for an open tube, but it's not anything you are expected to know. And then lastly, we talked about sound intensity, how the loudness of a sound, and our equations for that, intensity being power per area, or power for 4 pi r squared, and then converting between decibels and watts per meter squared, right? Intensity I is in watts per meter squared. Right here, watts per meter squared for I. And then for beta here is in decibels. So our 2 different units for sound intensity. If you have any questions, always feel free to reach out. We have now covered all of the content on Unit 7. So Friday, which is now not a C day, but a full B day, we will do a bit of review. We'll recap, we'll look at all those things. And I know we do have spring break coming up. So when we get back from spring break, we'll have that Tuesday to continue that review. And the Tuesday after spring break is when our quest is due as well. So if you have a great day, and please feel free to reach out if you have any questions. Thank you.